We're going to go on and talk about carbonate equilibria just because it's a good example to work with, and it's valid for soils and natural waters and just about anywhere in the Earth's surface environment. Okay, so usually we find bicarbonate dissolved in natural solutions, whether they're in a soil or in a stream or in the ocean, whatever. Rainwater even. Rainwater pH is around about 5.6 because of this acid dissolution reaction of carbon dioxide dissolved in water. So the atmosphere, this slide is obviously a bit dated now. The atmosphere has now reached 400 parts per million CO2, but it's still true that the soil gases, for example, have much higher CO2 concentrations. And one of the main things affecting carbonate equilibria is the presence of calcium ions. So if the concentrations of both calcium ions and carbonate ions gets high enough, then we precipitate calcium carbonate or calcite because it has a relatively low KSP value, about 4 by 10 to the minus 9, so quite a small number, not as small as some solids, but definitely small. Okay, so we can plot a similar sort of diagram to the one we saw for phosphate for the carbonate system as well. So percent of species, often we'll see this as an alpha value between 0 and 1, or in this case percent between 0 and 100%. It's the same thing really. A more realistic pH range perhaps for natural environments here, although 12 is a little high. Just showing the change in concentration with species at pH. So CO2 dissolving in water gives carbonic acid, which as pH increases progressively dissociates to give bicarbonate in natural systems. Bicarbonate would be the predominant carbonate species above pH 6.5 or so, and below about pH 10.5. And at very alkaline pH we see carbonate, the divalent form of carbonate, being predominant. Okay, now that's an acid-base sequence of reactions. It doesn't really matter, but what we're going to do is use that sequence of reactions to understand how systems work. Here's another way of looking at it, and often you'll see pH predominance diagrams actually plotted on a logarithmic scale, because then we can see species which are present at low concentrations. So I'll just flick back up to the previous diagram. It would appear that once we reach about pH 9.5, that H2CO3 disappears from the system. Well, disappears is not really true in real life. It just has very, very low concentration. So we can see this green line here at pH 9.5. It hasn't disappeared from the system. It's sitting around 10 to the minus 7 moles per litre, which is nearly zero, but it still keeps decreasing, at least that's what equilibrium theory tells us. Alright, so there's a bunch of other species on this diagram because we've popped in one more component, and that's calcium. So instead of going from a just carbonate plus water system, we're now a carbonate plus calcium plus water system, and it adds quite a bit of complexity, not the very least because we see a decrease in the total concentrations caused by precipitation of calcite, and just restricting that to an environmental pH range. But we can see from that in theory, at least, depending on the overall concentrations of various things, and we have to usually fix concentrations of our components for a calculation like this. We can see that calcite precipitation is quite likely under many environmental conditions and starts to occur in theory at about pH 8. Alright, in natural waters then, just generalizing a little bit for a start, we can see that carbon exists as the carbonate species that we've seen, but also as various forms of organic carbon. And there are a range of species for most other elements in natural systems. Nitrogen has a lot. Nitrate, nitrite, ammonium, dinitrogen gas or dissolved gas, organic forms, and even ion associations or ion pairs, a form of weak complex, so the ammonium sulfate ion pair. and so on. So the phosphate ones we've seen already, and we'll perhaps come back to these sort of ideas. Alright, now I did mention at the beginning that we need to understand species versus total concentrations and mass balances and things. So when we measure something in a solution, for example the solutions you extracted from soils the other day using DTPA, we subject it to some sort of analysis. In the old days we used to use something like this called atomic absorption spectroscopy. These days we tend to use ICP, and because ICP you can measure multiple elements at once. We've just run out of time with atomic absorption. However, what we're doing there is we're converting all species into ions in the case of ICP, where they emit light, and so we're removing any speciation just because of the high energy causes breakdown of just about everything, either in a flame or a plasma. However, that total concentration which we've measured in particularly a natural water sample will have been made up of a range of different species. So total copper we define as the sum of its species. And if we go back to the previous table, we would have seen that for copper, the main species in natural waters, including soil solutions, would be just divalent copper ions, a copper sulfate ion pair, a hydrolyzed copper species or hydroxyl complex, and a complex with carbonate. And in many systems we'd probably add a complex with dissolved organic matter to that, and that's what we call a mass balance equation for copper. Okay, we're going to use those a little bit later on to show you how speciation calculations work. Alright, so carbonate reactions, we're going to continue on with that. So we've seen the acid-base reactions. We also need to consider another reaction. First of all, the dissolution of calcium carbonate. So calcium carbonate will be in equilibrium with a certain concentration of carbonate ions depending on the calcium ion concentration, because the KSP or dissolution equilibrium constant is defined by this expression here. The calcium concentration times carbonate is equal to some fixed amount. So the higher the calcium concentration, of course, the lower the carbonate concentration can be. We also know that carbonate can react with water, and that's a reaction which would tend to raise the pH. Carbonate is more strongly basic than water, so it can grab a hydrogen ion off the water molecule to form bicarbonate, and we get hydroxide in solution, a slightly alkaline solution usually. So to fully characterize the carbonate system then, there are a bunch of reactions that we need to consider. There's the reaction of water with carbon dioxide gas dissolved in the water to produce carbonic acid, and we can define that in terms of an equilibrium constant. We're going to call that KH, and the minus log version of it pKh. The dissociation of carbonic acid has an acid dissociation constant associated with it. Likewise, the dissociation of bicarbonate, and also the solubility of calcium carbonate, which we've seen above. Okay, so there are 4 reactions that we need to consider, and we have 4 reactions. We've got some known values of equilibrium constants, and that allows us to calculate the speciation from the system. Alright. So, because we know the equilibrium expressions, that is, the equations which define each equilibrium constant, for example here for the dissociation of carbonic acid or the dissociation of bicarbonate, we've got pretty much an algebraic equation which defines the first and second acid dissociation constant of those, and we can combine those 2 reactions to give the overall dissociation of carbonic acid. Remember that to do that we multiply the equilibrium constants, or we can just add the log K values. Alright, and we can also define a mass balance of total inorganic carbon or total carbonate, which would be CO2 plus HCO3 plus CO3. Often we shorthand these, so you can see that I've omitted the ionic charges from bicarbonate and carbonate just to make things a little bit clearer to read and easier to write, obviously. Okay, so for any species X, our alpha value is X over the total concentration. So in this example, the alpha values for each of the separate species equals 1, right? Now, we can further write an algebraic expression for each of those alpha values. Okay, so Ct is defined by the sum of all concentrations, and CO2 is just CO2. And from the previous equations, which defined the equilibrium constants or the acid dissociation constants, we can actually express bicarbonate in terms of carbon dioxide concentration and hydrogen ion concentration, and likewise for carbonate we can express that in terms of carbon dioxide concentration and hydrogen ion concentration. Alright, so we're building on something here. So we substitute those two expressions in and do a bit of algebra on that to simplify the expression. We find that the fractional contribution of CO2 to total carbonate is an equation which only includes hydrogen ion concentration and the equilibrium concentration, equilibrium constant values. Now we know K1 and K2, so then our alpha value or fractional contribution of CO2 is only a function of hydrogen ion concentration. In other words, it's only a function of pH. Okay, so that's how we do that. And you can do the same sort of algebraic wizardry for alpha HCO3 and alpha CO3 2-, and you get similar looking expressions, but obviously they're not all exactly the same. So just to reinforce that, we only need to know the equilibrium constants, 2 of them, and pH, and from that we can calculate 2 unknowns. We actually don't need to calculate the third one because they all add up to 1 by definition. Alright, so that can be a useful check on the system. Right, and that's how we can derive the carbonate pH predominance diagram. Now that I did mention that we would come to this, I'll go through this fairly quickly, how we deal with the differences between activity and concentration. So, first of all, activity, which is the parameter which we actually use to define equilibrium constants, not actually concentration. They're not always equal, and that's particularly the case if we have high salt concentration in our solution. Now, activity is related to concentration, so the activity of any substance dissolved in water, X, is equal to its concentration times an activity coefficient, which are usually constrained to be between 0 and 1. And as the ionic strength or dissolved salt concentration, as the system becomes more dilute, basically, as the system becomes more concentrated in terms of salts, we see that our activity coefficient decreases. So there's a lot of difference between activity and concentration at high ionic strength. Now, fortunately, there's plenty of theory surrounding this, and there are a number of different equations which allow us to calculate our activity coefficient, these gamma X values, from the ionic strength. Now, they're all valid under slightly different conditions. Often we use the Davies equation because it has a wide range of applicability to different ionic strengths. Doesn't cope very well with very high ionic strength, where we tend to use something called the Pitzer equation. Alright, so our ionic strength is defined by this. It's half the sum of the charge on the ion, Z squared, times its concentration for every single ion that's dissolved in our solution, so that we can convert concentrations to activities, or we can adjust the equilibrium constants. Alright, now that's probably enough on that, just to show you that it is possible, and if you're worried about that, there are ways of dealing with it. In fact, the software that we will use does that. It calculates ionic strength, and we'll use, I think, the Davies equation usually to calculate out gamma values for each ion and make the necessary corrections. It's also a little temperature dependent. Okay, so often what we find in the literature are what we call stability constants, which are valid only for a certain temperature, ionic strength, and a particular type of background electrolyte even. As long as we know the conditions, we should be able to correct for them. Okay, so in general, what does equilibrium modelling do? Well, first, if we know all the reactions, and that's sometimes a big ask, and we know all the equilibrium constants for those reactions, we can apply similar principles to those which we saw for the carbonate calculation just now. We can apply that to very, very large numbers of components. So, just to remind you, in our carbonate system, we really only had two components, and one of them we assumed that we knew, that was hydrogen ion concentration, and we had one component carbonate. But there are mathematical techniques based on matrix algebra and iterative solution of equations by which we can do this type of calculation for very, very complex systems, and we'll find that out hopefully when we do our practical exercise. Okay, so we definitely include solid phases, and as I mentioned, the program that we're going to use is one called PhreeqCi. It's freeware from USGS. Now there are a bunch of different speciation codes that you can use. Some of them you have to pay for, some of them you don't. But I'm quite fond of PhreeqCi, and it has been continually updated since it was developed quite some time ago by the United States Geological Survey, and of course, as with anything that the United States government produces, it's free. So, let's move on. Again, we've got some character glitches here, never mind. So that's what we've seen before. The sorry, accidental scrolling there. The carbonate system. So we just did a calculation for this, and this doesn't look too dissimilar from what we looked at because of the the calcium concentration. This system being quite low. If we bump up the calcium concentration, we're likely to exceed the solubility product for calcite. In fact, we see calcite precipitation beginning at around pH 7.5 in this example. The mathematical procedure looks something like this. Our input needs to be, we often express them in terms of metals and ligands. This is from Speciato's textbook, this schematic. But it doesn't have to be. We can show you an example of that, but you can think about the carbonate system as being a ligand carbonate, and we can add a metal to that, calcium. It makes conceptual sense. What we need to do is formulate mass balances for every possible component, so their total concentration is the sum of their species. Right? And we do the elimination of complexes. That's that stage where we substitute the algebraic form of the equilibrium expression into our mass balance. And usually at the beginning of the program we also have a guess at what the free ion concentrations are. And then the number crunching engine in our software will estimate the free ion concentrations from the algebraic equations, or a large system often of algebraic equations. And once we have an estimate of the free ion concentrations, we can calculate the concentrations of all the species and complexes, and add them up and see if they match our totals. If they do, then we've reached a solution. If they don't, then we get some better guesses of free ion concentrations and pop them back in and keep on going round, usually several times before we finally end up with output that is internally consistent, and that we have convergence in the system. Alright, So that's how it works, and here's an example of the output of a speciation calculation in slightly tidier form than you'll see output from PhreeqCi, but less information than we'll see from PhreeqCi as well, where Speciito presents speciation for an acid soil solution. And we can see, for example, that calcium ions are present mostly as the free ion. There's a little bit of calcium present as an ion pair with sulfate. That reflects the reasonably high concentration of sulfate in the system. And these are only the predominant species. You'll notice that calcium sulfate ion pair is not one of the dominant species for sulfate. There are some ions which don't speciate, if you like. Chloride, known not to combine so much with other ions, but aluminium, for example, forms very strong complexes. There's pretty much no free aluminium ion in the solution, despite the fact that it's an acid soil solution. It's present mostly in complexes with organic ligands and fluoride, and so on. So that's the type of information that we can get out. Okay, I'm going to flick through this. If you want to read through this, I'll just leave it on the screen for a while. I'll put a PDF as well on LMS, basically going through the same type of procedure as we did for carbonate. We're just having a slightly more complex example. That's a slight play on words because we're looking at formation of a copper glycine complex with the amphoteric ligand glycine. So it's an amino acid which can both accept and lose hydrogen ions. Again, we calculate mass balances, we do our substitutions. Again, we end up with two equations and two unknowns, and so on. Okay, so that's the process now. There are some limitations to speciation calculations, as you would expect. Nothing is perfect. First of all, we assume that the system comes to equilibrium, or has come to an equilibrium, that our modelling then is valid, and that in many natural systems is not the case. There are things leaving and entering the system all the time in terms of chemistry. Our measurements may be wrong. Well, seeing our modelling is based on some measurements, total concentrations, for example, that can be quite a valid criticism of equilibrium modelling. We may not know all the reactions. For example, some of the reactions with natural organic matter are pretty poorly defined, and it also depends on where the organic matter comes from. This last one may not include redox reactions, a bit of a furphy. PhreeqCi does, and most contemporary software does. However, the way that we correct equilibrium constants for temperature, there may not be enough information to do that. Often there is, but often there's not. Activity coefficients, usually the software will be able to calculate activity coefficients adequately. It may not be perfect, but it may be good enough. What we generally see is that speciation models tend to be more successful for purely aquatic, so just where we have a solution that's not in contact with solids or not influenced by solids, compared with one that is, for example, the pore water of soils or sediments. And that's partly a function of having fewer reactions, and therefore we're more likely to know all the equilibrium constants for the relevant reactions. Just a couple of examples where speciation calculations fall down. This is a fairly basic example showing the PZN, so minus log zinc concentration. So zinc is actually increasing as we go up the vertical axis as a function of pH, which we know about. And if we look at the theoretical relationships based on solubility of different types of zinc compound which might exist in soils, we find these particular relationships. But if you actually measure zinc concentration in solution versus pH for real soils, you get quite a different relationship. First of all, they at any one pH value, it seems like the concentrations of zinc in solution are much lower, so there are obviously other types of reactions going on, probably adsorption reactions, which are removing zinc from solution more strongly than formation of a solid does, but also some odd looking pH behaviour. For example, high concentrations of zinc and higher pHs, we're getting an increase in zinc concentration as the pH increases, possibly related to the solubilization of formerly solid organic matter in soils, which can then carry zinc into solution as a zinc organic complex. Just a guess. Another example which we've had a look at already. So this relates probably both to the problems with measurement, in this case of free iron concentrations of cadmium, copper, nickel and lead in two different environments. So you can measure the uncomplex metal ion in solution by different types of technique, or you can model it based on the total concentrations and the other compositional properties of that system. And as we've noted before, sometimes they agree reasonably well, although do note this is a log scale for concentration, so any differences are pretty large differences, and in this particular environment like Gryphon, there are very large differences between modelled and measured. So 3 or 4 orders of magnitude difference between copper concentration, depending on whether you measure it or model it, and whether that's a shortcoming of the measurement techniques or the modelling techniques or both, we don't really know. So there's a start.